Let's go, Mr. Yellow Giraffe Man!
It's time for Maths with Mr. Thomas.
Chapter 10, lesson number 7, the inverse of a matrix. Bum bum bum. So let's say we have these two matrices here. We've got matrix A with the entries 2, 1, 3 and 2 and matrix B with the entries 2, -1 and -3 and 2. Let's say we wanted to multiply them together, so we wanted the matrix A times B. Could we do that? Well, matrix A is a 2 by 2 matrix, so that's 2 times 2. Matrix B is a 2 by 2 matrix, 2 by 2 as well. And remember, when you multiply matrices together, these numbers in the middle beside one another have to be the same. They are, so we can multiply the matrices A and B. The resulting matrix, where we're left with a 2 at this side and a 2 at this side, so the resulting matrix will be a 2 by 2. If we set that up, so matrix A times matrix B, we know we've got a 2 by 2 matrix. And to work out the entries, well, to work out this entry, which is in the first row and the first column, you multiply the first row by the first column. So 2 times 2 plus 1 times -3. To work out this entry here, which is in the first row and the second column, you multiply the first row by the second column. So 2 times -1 plus 1 times 2. Going down a row, so second row, first column, to work out this entry here, well, second row, first column, so you multiply the second row by the first column. So 3 times 2 plus 2 times -3. And finally, this entry here, it's in the second row and the second column, so you multiply the second row by the second column. So 3 times -1 plus 2 times 2. If you work that out, you will end up with the matrix with the top row 1, 0 and the second row 0 and 1. Bum bum bum! You are perfectly right. That is the identity matrix. And your identity matrix you could just write as I. Let's say we decided to flip that. Let's say we worked out the matrix B times matrix A. Could you do that? Well, once again, matrix B is a 2 by 2 matrix, 2 by 2. Matrix A is a 2 by 2 matrix, 2 by 2. And the numbers in the middle have to be the same. The numbers in the middle are the same, so we can multiply them together. And the resultant matrix, woo, will be a 2 by 2. So, matrix B times matrix A. Matrix B first of all, then matrix A. We know we've got a 2 by 2 matrix, so to work out this entry here, well, that entry is in the first row and the first column, so we multiply the first row by the first column, so 2 times 2 plus -1 times 3. Moving along, this entry here in the first row, second column, you'd multiply the first row by the second column, so 2 times 1 plus -1 times 2. To work out this entry here in the second row and first column, you multiply that second row by the first column. So -3 times 2 plus 2 times 3. And finally, this last entry in the second row and the second column, multiply the second row by the second column. So -3 times 1 plus 2 times 2. Working that out, what does that give you? Good, that will give you 1 and 0 in the top row, and the second row, 0 and 1. You're right! Once again, it is the identity matrix. Woo! Which means then that matrix B is known as the inverse of matrix A. Because if you multiply them, matrix A times matrix B or matrix B times matrix A, you end up with the identity matrix. The inverse of matrix A is denoted again by a capital A, but to the power of -1. So if you see a matrix with a capital A to the power of -1, it means the inverse of that matrix A. Only square matrices have an inverse, however, it is not all of them. And to determine whether or not a matrix has an inverse, it all comes down to the determinant. If the determinant of a square matrix is non-zero, so if it's not 0, then it means an inverse exists. And in that case, you would say that the matrix is invertible or non-singular. The inverse of matrix A is such that if you take matrix A and multiply by its inverse, so A to the power of -1, you end up with, good, you end up with the identity matrix. And also if you flip them, so the inverse times A, well again, you end up with the identity matrix. What do you think it means though if you work out the determinant of a square matrix and you get 0? What could you say about the inverse? Good. If the determinant of a square matrix is 0, then it means an inverse does not exist. So this matrix would be said to be non-invertible or singular. And finally, sometimes an inverse matrix can be found from a given matrix equation. So if you have a matrix equation, if you can rewrite it in the form of a matrix times another matrix equals I, then it means then that, well, if you have A times B equals I, then B would have to be the inverse of matrix A. And it's because if you have matrix A multiplied by its inverse, you end up with your identity matrix. So to sum that up, if the determinant of matrix A is 0, then there is no inverse. The matrix is singular and it's non-invertible. If the determinant is not equal to 0, then it's non-singular and it means an inverse does exist. It is invertible. Let's look at some examples then. So example 1, let matrix A equal this matrix here with the entries 2, 4, 1, 3. Part A, show that the matrix A is invertible. Part B, show that A squared equals 5A take away 2I. And part C, hence obtain the inverse matrix A to the power of -1. So for part A, how do we show the matrix is invertible? Well, if it's invertible, then the determinant of that matrix is not equal to 0. So how do we work out the determinant of this matrix? What do you do, Sandy? Brilliant. It's going to be AD take away BC. So it's going to be the 2 times 3 take away the 4 times 1. And if you work that out, Sandy, yes, you get 2. And that means because the determinant is not equal to 0, then the matrix is invertible. An inverse would exist. Part B, show that A squared equals 5A take away 2I. And again, this was just our matrix, matrix A. So A squared is going to be matrix A times matrix A. Can they be multiplied together? Well, you know matrix A is a 2 by 2 matrix. Again, you know it's matrix A, it's a 2 by 2 matrix. The numbers in the middle are the same, so it's 2 and 2. So they can be multiplied, and the result will be a 2 by 2 matrix. So matrix A times matrix A, we'd have the 2, 4, 1, 3, just multiplied by itself. The result's a 2 by 2 matrix, so to work out this entry in the first row and the first column, you multiply the first row by the first column. So 2 times 2, add on 4 times 1. To work out this entry here in the first row and the second column, multiply the first row by the second column. So first row by the second column. So 2 times 4, add on 4 times 3. To work out this entry here in the second row and the first column, multiply the second row by the first column. So 2 times 1 plus 3 times 1. And to work out this entry here, which is in the second row and the second column, multiply the second row by the second column. So 1 times 4 plus 3 times 3. Working that out, and you end up with the matrix with entries 8, 20, 5, and 13. So that is what A squared will be equal to. We're asked to show that's equal to 5A take away 2I. Well, 5A take away 2I is going to be 5 times matrix A. Take away 2 times, what's I? Good, it's the identity matrix. So we'd have 5 times matrix A, take away 2 times your identity matrix. To multiply this matrix by 5, you just multiply each entry by 5. So 5 times 2, 5 times 4, 5 times 1, 5 times 3 will give you this matrix, and you're taking away, and then again multiply each entry here by 2. So you'd have 2, 0, 0, 2. To subtract, you want to subtract the corresponding entries. You'd have 10 take away 2, which gives you 8, 20 take away 0, 20, 5 take away 0, 5, and 15 take away 2, 13. We can see that A squared is this matrix 8, 20, 5, 13. 5A take away 2I is also 8, 20, 5, 13. So we can say that A squared equals 5A take away 2I. Woo! High five. Part C, hence obtain the inverse matrix A to the power of -1. We had our matrix A, and we just worked out in part B, A squared equals 5A take away 2I. Now to work this out, remember, because A times its inverse equals I, or the inverse of A times A equals I, if we can rewrite our equation to be of the form A times something equals I, that something has to be the inverse of matrix A. So if we can write it in the form A times B equals I, we can easily read off the inverse. So we're starting with this equation that we just had in part B. A squared equals 5A take away 2I. Now we need A times something equals I. So to get that, let's get the A's to one side and the I's to the other. So subtract 5A from both sides will give us A squared take away 5A. equals negative 2i. We're wanting it to equal I and not the negative 2i. Well, let's get 2i first of all, so deal with the negative. Let's multiply through by negative 1. So we'd have negative a squared plus 5a. If you rewrite that with the positive term first, you'd have positive 5a take away a squared, and that would equal, multiply the negative 2i by negative 1, and it will give us 2i. Again, we need a times something equals I. Let's deal with the left-hand side. We need it in the form of a times something. How could we go about doing that? Good, you could take out a as a common factor. So if you take out a as a common factor, well, it's going to be a times 5. But you're not just going to have it with 5. You can't just have a number. You need it in the form of a matrix. But remember, you could have it as a times 5i, because I just acts like the number 1, but it's a matrix. So you can write that as a times 5i. That would be take away. Well, to get a squared is a times a, so it becomes 5i take away a. And that would equal 2i. And again, you wouldn't just have a times 5 take away a, you need it with a matrix. But ai is just equal to a, so it's bringing in that matrix. Because of this, we have a times, and if we divide both sides by 2, well, we're really dividing this by 2. But let's keep the a out as a common factor, and let's say it's a times half, and then we've got that 5i take away a, and that would equal just I. So we're dividing both sides by 2 and multiplying by the half. So we've got a times half times the 5i take away a. From there, because we've got it in the form of a times something equals I, we know that something has to be the inverse. So we can say then that the inverse of matrix A is equal to a half of 5i take away a. But we're not finished there, because we actually want to obtain that matrix. We want the matrix with the entries. We don't just want to say it's a half of 5i take away a. So where do we go next? Well, after that, you have to work out what that would actually be. So let's deal with 5i take away a first of all. So 5i take away a, well, that's 5 times your identity matrix. So 5 times 1, 0, 0, 1, take away matrix A. And again, up here, this was just matrix A. Because we're multiplying the matrix by 5, you're multiplying every single entry by 5. So 1 times 5, 0 times 5, and so on. So you'd have 5, 0, 0, 5, take away the 2, 4, 1, 3. And if you subtract, just subtract the corresponding entries. So 5 take away 2, 0 take away 4, 0 take away 1, and 5 take away 3. So that's 5i take away a, but remember the inverse was equal to a half of 5i take away a, so it's going to be a half of this matrix here. And if you multiply through by a half, well, your top row then would become 3 divided by 2. You'd have negative 4 divided by 2. You'd have negative 1 divided by 2, so negative half, and 2 divided by 2, which will give you 1. So the inverse of matrix A will just be the 3 over 2, negative 2, negative a half, and 1. Woo! Example 2, let matrix A be this matrix here with these entries 1, 1, 1, 1, 2, 3, 1, negative 1, negative 1, and matrix B be this matrix 1, 0, 1, 4, negative 2, negative 2, negative 3, 2, 1. By considering the matrix product AB, obtain the inverse matrix A to the power of negative 1. So because we want the matrix product AB, we have to multiply these matrices together. First of all, again, just to check, can we do that? Well, matrix A is a 3 by 3 matrix. Matrix B is a 3 by 3 matrix. The numbers in the middle have to be the same, 3 and 3, which they are, so we can multiply them together. And the resulting matrix, woo, will be a 3 by 3. So we can multiply them together. So we've got matrix A times matrix B. We know we've got a 3 by 3 matrix, so we would have something that looks like this. To work out this entry here, which is in the first row and the first column, you multiply the first row by the first column. So 1 times 1 plus 1 times 4 plus 1 times negative 3. To work out this entry here, which is in the first row and the second column, you multiply the first row by the second column. This entry here in the first row, third column, multiply the first row by the third column. This entry here, second row, first column, multiply the second row by the first column. This entry here, second row, second column, multiply the second row, 1, 2, 3, by the second column, 0, negative 2, and 1. This entry here, second row, third column, multiply the second row, 1, 2, 3, by the third column, 1, negative 2, 1. And this entry here, which is in the third row, first column, multiply the third row, 1, negative 1, negative 1, by the first column. This entry here, which is in the third row in the second column, multiply the third row by the second column. And this entry here, which is in the third row in the third column, multiply the third row by the third column. So 1, negative 1, negative 1 times 1, negative 2, 1. If you're unsure about the matrix multiplication, look back to the lesson that is on that. If you work that out, then the top row becomes 2, 0, 0, the second row becomes 0, 2, 0, and the third row becomes 0, 0, 2. Where could you go from there? What could you do, Amna? Perfect, you could take out 2 as a common factor, so if you do that, you'd have 2 times the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. But this matrix here, what's it known as, Amna? Identity matrix. Perfect, so you'd have 2 times I. It's 2 times your identity matrix. How does that help you? Well, by considering the matrix product, obtain the inverse matrix a to the power of negative 1. Well, we know from here that we'd have a times the inverse equals I. And for this, we've got AB equals 2I. So let's go over the page for that. We know that AB equals 2I. We just saw that. So we want a times something equals I. In order to get I, we'd have to divide by 2 or multiply both sides by a half. So we'd have a half of A times B. But if we take the A first, then it's going to be A times a half B, and that would equal I. So we know then that the inverse of matrix A is going to be a half of matrix B. So it's going to be a half times just what that matrix B was. Which means then the top row, if you half the 1, the 0 and the 1, you'd end up with a half, still 0 and a half. The next row, if you half the 4, the negative 2 and the negative 2, you'd end up with 2, negative 1, negative 1. And if you half the negative 3, 2 and 1, you would have negative 3 over 2, 1 and a half. So that there will be the inverse matrix a to the negative 1. Example 3, find the values or value of k for which the matrix A with the entries 3k2, 3, negative 4, 2, k0, 1 is singular. Bum, bum, bum. What does it mean if it is singular? Perfect. A matrix is singular when its determinant is 0. This is something we were looking at earlier. So if it's singular, the determinant equals 0. So we need to work out the determinant. So the determinant of matrix A will equal. How do you work out the determinant? Well, you want to take that first entry in the top row, the 3, and you eliminate its row and column. So if you take the 3, eliminate that row and column, you're left with this little matrix here, this 2 by 2. So you'd have negative 4, 2, 0 and 1. And what you do is you take the 3 and you multiply it by the determinant of that remaining matrix. Remember, you would have the plus minus plus pattern when you are dealing with this. So you'd have take away, and the next entry would be k. So it's take away k times. And again, you eliminate that row and that column. So eliminate the row, eliminate the column, and you're left with the matrix with 3, 2, k and 1. So you want to work out the determinant of that. Then you take the last entry in the top row, again the plus minus plus pattern, so it's plus 2 times. And if you eliminate that row and that column, eliminate the row, eliminate the column, you're left with 3, negative 4, k and 0. And we know that the matrix is singular when the determinant is 0, so you can say that equals 0. From there then, it's going to be 3 times to work out the determinant. Here, you're going to have negative 4 times 1, take away 2 times 0, which will give you negative 4. We've got take away k times, and the determinant of this, AD, take away BC, will give you 3 times 1, take away 2 times k. So 3 take away 2k. And then we'd have plus 2 times 3 times 0, take away negative 4 times k, which will give us 0 plus 4k. And again, that equals 0. Multiply the brackets, that gives us negative 12, take away 3k plus 2k squared, plus 2 times 0, just be 0, plus 8k equals 0. Rearrange that so we get 2k squared plus 5k take away 12 equals 0. And to solve that, we need to factorise. Factorising that will give us 2k take away 3 bracket k plus 4 equals 0. And if 2k take away 3 was equal to 0, if you add 3 to both sides, 2k would equal 3. Divide by 2, then k would equal 3 over 2. And if k plus 4 was equal to 0, then k would equal negative 4. So we know that this matrix here will be singular, the determinant would be 0, when k equals 3 over 2 and negative 4. Try these questions in the Unit 3 booklet. You're on page 25 and 26. Check your answers as you go. Best of luck, have fun, enjoy, bye. Woo! Yeah.